For the last decade, Apache Parquet has defined data lake architecture. It was built specifically for aggregate SQL queries and efficient sequential batch scanning. But modern machine learning pipelines operate differently. Training a large language model or processing multimodal datasets requires pulling massive multidimensional arrays and executing random batch sampling across billions of parameters. Applying Parquet's legacy sequential design to randomized ML workloads creates a severe I/O bottleneck. Traditional file formats cannot decode data fast enough, leaving expensive GPUs idling and starved. The compute hardware is ready, but the file structure limits throughput. Keeping those GPUs saturated requires a different data architecture. 3 specific open-source formats, Lance, Nimble, and Vortex, were built to address this exact throughput gap. Adding more compute will not solve a storage bottleneck. To achieve linear scaling in AI training, the industry is moving towards these specialized file structures. The core issue begins at the atomic level of traditional columnar storage, the row group. This is how Parquet bundles and compresses its data. Machine learning training relies on random batch sampling. The algorithm must pull individual rows from completely different, randomized locations across the dataset instantly. Here, the mechanical trap is clear. Parquet is stored as a single compressed block, meaning you cannot extract a single row in isolation. To read a target row, the system decompresses the entire block, extracts the needed line, and discards the rest. When an ML model executes this type of random point access millions of times per second, the wasted decompression overhead creates massive latency. The open-source format Lance was engineered to eliminate this specific architectural flaw. Lance re-engineers the columnar layout to isolate the data. When the system requests a target row, it instantly extracts it from the block without triggering a full decompression cycle. This structural adjustment allows Lance to deliver random access speeds up to 1,000 times faster than Parquet. For machine learning, random access is a primary performance requirement, not an edge case. That requirement changes how data must be laid out. Shifting from row depth to column width reveals another bottleneck. Modern AI workloads utilize wide feature tables and vector embeddings, arrays composed of thousands of floating point numbers. Older formats use heavy metadata frameworks to track schemas. This approach works for traditional SQL tables with 50 or 100 columns. When a query parser tries to map tens of thousands of features using legacy metadata, it hits a wall. The parser itself stalls while trying to navigate the schema before the data even moves. Nimble, developed by Meta, was engineered to handle these extreme-scale feature tables. Nimble replaces heavy schema maps with a minimalist metadata structure built on flat buffers. This allows the query engine to map the massive grid instantly. At this scale, the choice of metadata format determines whether the training run can physically begin. Lightweight metadata is a requirement for high-dimensional models. This visualization represents the traditional hardware decoding pathway, a legacy process that creates significant compounding friction for modern AI workloads. In this pipeline, data moves from the disk into memory, but must be decoded by the CPU before it is handed to the GPU. In machine learning, this CPU decoding overhead caps the speed at which models can train, regardless of how much GPU power is available. Formats like Vortex and Nimble use a zero-copy architecture to remove this bottleneck. By utilizing direct memory mapping, the data on the disk is already in the layout the GPU requires. The CPU decoding step is bypassed, creating a direct path for the data. These formats also utilize SIMD, single instruction, multiple data, leveraging modern hardware to process multiple data points simultaneously. By prioritizing hardware utilization, AI-native formats ensure that I/O overhead never outpaces the actual compute power of the GPUs. Standard legacy workflows for vector embeddings are split. Teams store raw data in Parquet, but must export those embeddings to a separate vector database for indexing and search. This setup creates operational friction. It requires maintaining 2 separate infrastructures and constantly syncing data across the network. AI-native formats collapse this architecture by moving the search indexes inside the file itself. Lance integrates vector indexes, like IVFPQ and HNSW, directly onto the disk. The search structure lives alongside the data. This enables zero-copy schema evolution, allowing teams to add new embeddings or metadata tags without rewriting the entire dataset. Native vector integration turns the storage format into a searchable database, removing the need for separate synchronization layers between storage and search. We are seeing a clear divide in the data format landscape, driven by specific workload demands. This matrix shows the current taxonomy. Text formats like CSV and JSON handle ad hoc APIs. Binary row formats like Avro manage rapid streaming. Parquet and Orc remain optimal for SQL analytics, but for extreme-scale AI, legacy formats hit a limit. Enter the AI native layer, Lance, Vortex, and Nimble. These formats replace batch-scanned files with zero-copy reads, SIMD accelerated hardware, and vector-native architectures. Because large language models demand high-throughput data delivery, the training pipeline is limited by the physical constraints of the file format. Choosing an AI native format is now a foundational requirement for scalable AI.